This section is going to be about solutions and also physical properties of molecules. So for example, we could ask the question, will a compound dissolve in water or will it dissolve in oil? So if we need to clean it up, do we need to use water or do we need to use oil? And also physical properties such as melting point or boiling point or density. How much heat are you going to need to get something to boil and turn into the gas phase? Other things that we can ask are, is a compound going to be present at room temperature as a solid or as a liquid or as a gas? And all of this is based on what are called intermolecular forces. And those are the attractive forces between molecules, not within the molecule itself, but actually between different molecules. And what we're going to do is understand how to recognize what those intermolecular forces are.
So these physical properties of compounds and molecules that we talk about are important when we talk about things like mixing. So for example, you might have some salad dressing, which has some oil floating on vinegar. And if you wanted to get those to mix, you would have to add something else. In the case of salad dressing, you would add something like mustard powder. But if you wanted to take something like oil and you wanted to mix oil with gasoline, there's going to be a prediction that you're going to need to make is, are they going to actually dissolve in each other? Because we know that if we took oil and we poured it into water, it wouldn't mix. And why is that? Well, those are the properties that we're going to talk about. And those properties can be very important if we wanted to change the melting point of water and ice, as an example. So, for example, in the winter, which is hopefully not coming too quickly, we want to move the snow off the streets, and we also want it to melt. And if we have it in our car, we want to make sure that the radiator of the car doesn't freeze solid, and so we would add some antifreeze to that water and make a solution. And if you were going to use your windscreen wipers in the winter, you would want to make sure that they didn't ice over. And so if you wanted to use that, you would need to add something to the water in the windscreen wiper fluid that was soluble in water, because if you just poured some oil in there, it wouldn't work. And so it's important to realize that these physical characteristics that we have, they are all related to a property called intermolecular forces. And so, for example, if you spilled some tea on your shirt, you'd want to know, well, how am I going to get rid of this? Would I use some type of oil-based solvent, or would I use water? And this is what's going to be important. So here, when we talk, for example, about a snowball, when you warm a snowball up, a snowball is made up of water molecules. Of course, we're always going to draw the bend now. When you warm a snowball up, what happens? Well, it melts, doesn't it? But the water molecule itself, the water molecule remains intact, because in ice, there's the water molecule, and in liquid water, there's the water molecule. So what actually happened? Well, there are some attractive forces between the water molecule and another water molecule. And what we're interested in now is, what are these types of attractive forces here that are holding these water molecules together? And those attractive forces are what we call intermolecular forces. And so intermolecular forces are the forces between molecules, so between the water molecules, as opposed to within the molecule, we have covalent bonds, and those are called intramolecular forces. And so chapter 10 goes into this in your book. And so what we're interested now is looking at these intermolecular forces. So here, if we take HCl as an example, and HCl, when we draw out HCl and we draw a Lewis structure of it, and we look at the molecule itself, we realize that it's a polar molecule, and this end is going to be slightly positive, and this is going to be slightly negative because of the difference in electronegativities that we talked about. And so there's one end of this is going to be slightly negative, and one end is slightly positive. And because chemistry is all about attraction, there's going to be an attraction between this negative end and this positive end of this other molecule. And so between the hydrogen and the chlorine is a covalent, extremely strong bond, but then there's this attraction between two molecules, and it's an attraction between a positive end and a negative end. And so intermolecular forces hold multiple molecules together. And so if we put lots of energy into this system here, we would overcome this attractive force because it's relatively speaking weak compared to the very strong force holding the hydrogen and chlorine together. And so it's rather obvious to understand that if you have a molecule that has a dipole, because if it has a dipole, it has a positive and a negative end, you could see that those could be attracted to each other because positive is attracted to negative. And so we have what are called dipole attractions. And dipole attractions are an example of an intermolecular force, so an IMF. And so if you want to know if a molecule has got dipole attractions, you would obviously look at it and say, well, does it have a dipole, which is the most important thing. And so just so you know, when you look at a liquid, between molecules in a liquid, there are always, so in this case, you could be looking at water molecules. There's a positive end and there's a negative end. So, for example, in the water molecule, this would be oxygen and this would be hydrogen. And there's going to be attractions between the positives and the negatives all the way through this liquid. And because of that, that liquid, those polar molecules in that liquid are going to be attracted to each other and they're going to be held together by dipole attractions. And you can break and reform these attractive forces as they travel through the liquid, as it flows through the liquid. And so if you look at two polar molecules such as HCl, there's a positive end and there's a negative end, and they're going to be attracted to their opposite charge. And so for a polar molecule, that is relatively simple. And so how do we know? Well, we have this table of electronegativities, the periodic table. And what it says is that if the difference, big delta, the difference between two molecules is greater than 0.4, then it's a polar molecule. So here between hydrogen and oxygen, the electronegativity difference 3.4 minus 2.2 is certainly bigger than 0.4, and so it's a polar bond. And so that's how we determine which bonds are polar. Now, interestingly, in this course, when we talk about polarity, the great thing is that most of the examples in important molecules that we talk about, if they're not the same element, so if it's not hydrogen bonded to a hydrogen or an oxygen bonded to an oxygen or a nitrogen bonded to a nitrogen, they're going to be polar bonds. And the only one that's of consequence that's important to realize is that carbon to hydrogen is non-polar. So most of the time, pretty much in this class, whenever you have dissimilar elements or dissimilar atoms, it's going to be polar. So for example, HCl is going to be polar, HF is going to be polar. But if you have CH, carbon to hydrogen, it's going to be non-polar. And why do we know this? Well, if we look here, this is carbon with an electronegativity of 2.55, and this is hydrogen, which is 2.2. 2.5 minus 2.2 is less than 0.4, so this would be a non-polar bond. And so there's a special case of polar bonds when you have a dipole. If you have a situation where you have a hydrogen atom that's covalently bonded to a highly electronegative atom like nitrogen, oxygen, or fluorine. And so the way I like to think about this is hydrogen to NOF. So if hydrogen, and this is the most important thing to remember, if hydrogen is bonded directly to nitrogen, oxygen, or fluorine, it will exhibit an additional polar attraction. And this additional polar attraction is called a hydrogen bond. And hydrogen bonding is very important in many biological systems because hydrogen is often bonded to an oxygen or a nitrogen in something like DNA or RNA or proteins. And so you might say, well, how do I remember that it's hydrogen bonded to NO or F? Well, if you look at the periodic table, here, these are the most electronegative elements, N, O, F. And these are the three most electronegative, and that's why they exhibit this special or extra polar attraction. And so I'm going to give you quite a few examples of those. And what basically happens is if you look at a water molecule, say in an ice structure, because that's when the molecules get nicely ordered, each one of the hydrogens here is attracted to this oxygen. This hydrogen is attracted to this oxygen. Why? Well, if you remember, this oxygen has got two lone pairs on it. So we can just put these lone pairs on here. And there would be this additional attraction between this hydrogen to this oxygen. And then, of course, each of those oxygens is going to be attracted to hydrogens in the opposite molecule or in another molecule, and thereby form a some kind of ice or crystalline structure. And so, well, you might say, well, this is all very well when you look at molecules that are polar, but what about if we look at a molecule such as carbon dioxide? And when we think about carbon dioxide, we draw the Lewis structure of carbon dioxide, and we would say, well, it has a polar bond here, but overall the molecule is non-polar. Now, if this molecule is non-polar, it means it doesn't have a positive end or a negative end. So there should be no attractions between carbon dioxide and another carbon dioxide. So if we had another carbon dioxide down here, there would be no attraction between them. Now, if we had no attraction between these carbon dioxide molecules, there's no way that we could produce a solid, because there has to be an attraction between those carbon dioxides to hold them together. But we know that solid CO2 exists because it's what's called dry ice. And here's a picture of dry ice. This is what dry ice looks like, and because dry ice exists, there must be an attractive force between this. And so when we talk about these molecules that are non-polar, there must be some type of attractive force. And what actually happens is that when these molecules, such as carbon dioxide, because they're continually vibrating, so molecules vibrate, they stretch, they rotate, they're continually moving. And when they do that, there's what's called a temporary dipole produced. And a temporary dipole is when, for a tiny split second, a nanosecond or a femtosecond, there is an unequal distribution of electrons. And when there's this unequal distribution of electrons, for a very small amount of time, the molecule has one end that's slightly positive and one end that's slightly negative. And it's only temporary. It's what's called a temporary dipole because it's only there for a very short period of time. And during that very short period of time, there's an attraction to another molecule, which is doing the same type of thing. And so this attractive force here, because it's between two molecules, is also an intermolecular force. And because it's between two molecules, we call it an intermolecular force. And these intermolecular forces, these are called dispersion forces. And dispersion forces, often called London dispersion forces, after Fritz London, who came up with the idea. These result from the formation of temporary dipoles, and they typically are present in non-polar molecules. And so here, this is a non-polar diatomic molecule. So, for example, it could be bromine, Br2, or it could be iodine, I2. So those types of molecules would produce temporary dipoles. And so these types of attractive forces, how do we know if they're strong or weak, or do they change? Well, if we look as an example, if we look at some organic solvents, this is called neopentane. It has 5 carbons and 12 hydrogens. and there's another molecule called isopentane, and then there's another molecule called N-pentane, and they all contain the same number of carbons and hydrogens. And if you look at the boiling points of these, the boiling points here, 9 degrees, 27 degrees, 36 degrees, which basically shows that neopentane would probably be a gas at room temperature, isopentane would be a liquid at room temperature, and N-pentane would also be a liquid at room temperature. And what we see is that the strength of these forces increase with contact area. So the shapes of these molecules become important when we talk about intermolecular forces. And so dispersion forces occur between non-polar molecules. And these molecules are hydrocarbons that are based on carbon and hydrogens. So this is methane. And if you end up going to 5 carbons, so C5, this would be called pentane. And these are examples of pentane. These are what are called isomers of pentane, which we will talk about a little bit more later. But as you increase the number of carbons and you change the shape of these molecules, the attractive forces between these molecules will change. And so the most important thing to realize is that intermolecular forces determine physical properties. So we're talking about physical properties, such as, why something is solid, a liquid, or gas at room temperature. So, for example, water, a liquid at room temperature, carbon dioxide is either a solid or a gas. Something like helium or neon in a balloon is going to be a gas at room temperature. And so we could ask these questions, such as paraffin, which is what candles are made out of, or water, or air if you heat it up enough. The temperature at the point at which those become gases is going to be important.